We are now going to talk about the wave properties of light. And there are several phenomena that occur with light that are explained by looking at the wave properties of light. So first of all, if we look at light waves from various views, we can see that light is a transverse wave, as is all electromagnetic waves. If you view them from the side, you see something that looks very much like a cosine wave. The direction of propagation is from left to right, and the direction of amplitude is from top to bottom, so they're perpendicular to each other. And the various views show you the various different ways in which you can understand light waves. Now, the Huygens principle is a principle that explains diffraction, and so let's take a look at this in more detail. First of all, we want to start over here, and we want to look at each wavefront as a point and how that wavefront results in the next wavefront, okay? And what you can see here is that at each point, it goes out as an arc. And because of that, its function is velocity times time. And so the propagation is in this direction. Each of these comes out as like a semicircle, and then you can imagine these being on top of each other. The Huygens principle states that every point on a wavefront is a source of wavelets that spread out in a forward direction at the same speed as the wave itself. And the new wavefront is a tangent of all these little wavelets that occur. Huygens' principle is applied to this straight wavefront, and it results in yet another straight wavefront. But each point emits a semicircular wavelet that moves a given distance. The Huygens principle, when it's applied to a straight wave that strikes a mirror, and the wavelets come in and strike this in such a way that each point strikes the mirror, and the tangent becomes of these wavelets form the new wave front that results in the angle of incident and the angle of refraction. And so when the angle of incident is from left to right, then the angle of reflection is straight down or perpendicular to that, as long as this mirror, of course, is at 45 degrees. So if we look at this in a more detail in terms of refraction, you see that if you have a straight wave front traveling from one medium to another in which the speed changes, the wave, of course, bends toward the normal or the perpendicular, and the wavelets themselves have a slower speed within the second medium, and that's why you have this bending. You can see the difference between V subscript 2t versus V subscript 1t and how that results in the bending in medium 2. Take a look at this for a minute or two just to see if you can get a sense of why this bending occurs and how this occurs. So, if we look at the principle of diffraction, and we look at A, we're talking about light. Now, when light passes through a doorway, it makes a more sharp outline with the floor. Since the light's wavelength is very small compared to the size of the door, it essentially acts like a ray, okay? On the other hand, if we look at sound, now sound, the wavelengths are much larger than light, and it bends to all parts of the room because of that. And this is the wave effect, because the wavelength of the sound is very similar to the size of the door, so it has a different effect. So what happens is even though the person is not in the gap created by the doorway, he is able to hear almost exactly the same as if he were standing in the actual path of the sound, whereas with light, very little light spills over because of the difference in the wavelengths. If you apply this to a straight wave front striking and opening, the edges of the wavefront bend after passing through the opening. And this is called diffraction. You can see because right at the edge of here, there's going to be a point where there's going to be that wavelet with the semicircle here and here. And that wavelet is going to proceed out and cause others in this way. Now, if the gap gets smaller, then this is the effect until you do get to a point where the gap is such that it's just the bent wavelet that comes through. So the amount of bending becomes more and more extreme as the opening gets smaller and smaller, and the wave aspects of this become more noticeable as this gap, or the hole in which this passes through, approaches the wavelength of the wave. So in order to take a look at this, Young did an experiment called the Young double slit experiment. And the double slit experiment, you send a light ray or a light on two slits. Now, this light ray has a pure wavelength. It's not white light. It's a light ray of a single wavelength. And it's toward a pair of vertical slits. And to look at the pattern of the vertical lines on a screen. Now, without diffraction or interference, there would be simply two lines on this screen. But because diffraction and interference both occur, you get a series of dark and light fronts that are caused by diffraction and interference. And so remember that if the two waves are in concord with each other, then they add to each other, and the interference is constructive interference. So you have this wave, these two waves together, the resultant wave is constructive, and it's twice the amplitude of each of the two composite waves. Conversely, if they're exactly off scale with each other or out of phase with each other, then you have perfect or pure destructive interference, and the resultant is a straight line. Now imagine that these are the two waves that pass through the slits. If for whatever reason they end up interfering constructively, you'll have a bright line. If, on the other hand, they interfere destructively, you'll end up with a dark line. And that's exactly what occurs. And we'll show you how this occurs. First of all, you have the rays coming, and they pass through the two slits. And then they end up with these wavelets, remember, due to diffraction. And then, as they spread out, independent of each other, you are going to end up with some areas of constructive interference, thus maximums, and some areas of destructive interference, thus minimums. And so, for example, as the light spreads out and diffracts from each slit, because the slits are narrow, the waves overlap and interfere with each other, constructively forming maximums and destructively forming minimums. But you can only see when it falls on the screen over here on C. The interference looks like this when it's passing through the medium, and then ultimately when it strikes the screen, you end up with a pattern that has these where some of this is the maximum constructive, then it becomes more and more destructive until you have nothing, pure destructive interference, and then constructive. But notice that this is less. Notice that this is less than this, and then another period of destructive, and then a very light out here. So what happens, and the reason this occurs, is because waves follow different paths to a common point on the screen. And here's the path from one slit, here's the path from the other slit, and here's the angle theta, which is the angle between the perpendicular between the two, from the slits to the screen and then to the single point. And so if you look at it, A results in destructive interference. As you notice, the waves become out of sync. Whereas when they arrive together, they're out of sync, so you end up with a dark or destructive line. B, on the other hand, are in sync. B, on the other hand, are in sync. And therefore you end up with a bright line. So how do we calculate this? Well, basically you look at the distance between the two slits. This distance results in a delta L, which is notice that this is the different path that each has to take. And delta L is going to be equal to D sine theta. Here's theta. Theta is the same, this angle and this angle are the same. So delta L is going to be D, the distance between the two slits, times the sine of the angle that these lines are traveling. Now this is obviously not drawn to scale. So, in some situations, straight out from this, delta L is 0, and it's bright. And then at the next bright, Y1 corresponds to theta 1. The next bright, Y2, corresponds to theta 2. And this is a pattern that the intensity falls off as you go out from the middle. So remember, d sine theta is equal to some multiple of the wavelength for multiples of 1 and minus 1, 2 and minus 2. So the center represents 0. The next is 1 and minus 1. The next is 2 and minus 2. And so let's look at a couple of problems now related to this. Now, when you talk about these, when m is equal to 0, it's called 0 order. When n is equal to 1, it's called first order. When m is equal to 2, it's called second order. It said is if the first order maximum of a pure wavelength of light falling on a double slit is at an angle of 10 degrees, what is the angle of the second order? Okay, so let's take a look at how we would do this. First of all, we have d sine theta is equal to m lambda. Now we know that d sine 10 degrees is equal to 1 times lambda. And we know that d sine something is equal to 2 times lambda. Because this is the first order, and this is the second order. So that means if this is 1 times lambda, we can substitute this for that. And so we have d sine of the new theta is equal to 2d sine 10 degrees. And the d's cancel out. So that means sine of theta, the new theta, the second order, is going to equal 2 times the sine of 10 degrees. Then theta is going to be equal 20.3 degrees. And then what is the highest order maximum possible here? Well, generally, now if you look at this first minimum, if you draw the triangle that's involved here, the point of first maximum is y, and this angle is going to result in a sine, or 10 degrees. Now the first minimum is exactly halfway between the first maximum and the zero. And so y is equal to the sine of 10 degrees. So 1/2 y is going to be the sine of the new angle, theta. And therefore, it's going to be the sine of 10 degrees divided by 2 is going to be the new. And the sine of 10 degrees is 0.1736. If we divide that by 2, and then we take the arc sine of that, we get 4.98 degrees for the first minimum. The last says, what is the highest order maximum possible? Well, you have m. If you solve the equation for m, you have m is equal to d sine theta over the wavelength. Now, in order to do this,